Hello and welcome everyone to Non-IITN. In this lecture, we are going to talk about a problem in metric space topology which had appeared in CSIR NET Mathematics February 2022. If you're enjoying the content, please don't forget to like, share and subscribe to Non-IITN. So let us quickly go to the problem statement. And the problem statement is the following. Let xd be a metric space and let f be a function from x to x such that the distance between fx and fy is less than or equal to the distance between x and y for every xy in x. Which of the following statements is necessarily true? Option A, f is continuous. Option B, f is injective. Option C, f is surjective. And option D, f is injective if and only if f is surjective. Okay, let us understand the problem statement step by step. So we know that this is nothing but the condition for Lipschitz, for a Lipschitz function, right? We know that distance of fx fy is less than equals to alpha time distance between x and y. This condition is satisfy a Lipschitz function, and Lipschitz functions are continuous. Here we have the Lipschitz constant to be 1. Nevertheless, this is a Lipschitz function, so it's just continuous, right? So option A is true. Now probably this was also a function, a question which had multiple options correct. Okay, so the inequality means that the function f does not increase distances, typically speaking. The distance between the images, so let me just skip this part. This is a definition for a non-expansive map or a Lipschitz continuous function with k equal to 1. Okay, let us analyze the other option. So option A is true, which we just claimed, and this is the immediate proof of it. You can also go by the sequential definition of continuity. It will be proven much easier than the epsilon delta definition. Okay, but the epsilon delta definition is also very easy, because if you choose the distance between x and y to be less than delta, then your distance between fx and fy will be less than epsilon if you choose epsilon to be delta. That's it. That's exactly the argument. Let us check the other options. Okay, the first option is f is injective. Now f need not be injective. Okay, so this is a particular example given to us in terms of the constant function. Something you should also know, that fx equal to sin x also satisfies this condition under the usual topology on R, because recall by the mean value theorem we know that the derivative of this is cos x and modulus of the derivative of x is less than or equal to 1. Therefore, what does the mean value theorem say? So it typically implies this, right? Equals to mod of f prime of zeta x minus y, where zeta is in xy, right? So if you choose fx to be sin x, then we will have the modulus of sin x minus sin y less than equals to modulus of cos zeta times x minus y, but this is less than or equal to 1, so this is less than or equal to x minus y. And we know that sine is not an injective function, because recall just recall the graph. You can deduce injectivity and surjectivity if you know the graph well. So the graph is in some sense like this, right? So if you just take a straight line through a point from along the y-axis, okay, sorry, parallel to the x-axis, you will see that there are multiple intersections of this line, right? So you have an intersection here, you have an intersection here, you have an intersection here, here and here. So obviously it's not injective, right? So it's not injective. And how do you claim surjectivity? Just try and think what is the shadow of the graph along the y-axis. So we know that the range lies between -1 and 1. So it's -1 and 1. So if you choose a point from here, let's say x is equal to -2, under sin x it has no pre-image. So it's not surjective as well, right? So let me just get back to the problem. So if you choose these two, then sin x and sin x just contradicts both these conditions, right? Disproves both these conditions. What about D? Now I would be very happy if someone comes up with an example of option D over the whole over the usual metric on R, but here we have an example on x equal to close 0 to open infinity under the metric subspace, as a metric subspace. Okay, because we are given an arbitrary metric space, right? I can obviously choose this, and I'm choosing the function f to be fx equals to x plus 1. Now clearly this function is injective, but this function is obviously not surjective, because what is the image of x? The image of x is 1 to infinity, which is not equal to x. For surjectivity I need it to be equal to x, because the function, recall, is from x to x, right? So therefore this function is not surjective, but it is injective, and it satisfies our condition, right? So therefore the fourth option was saying that the function will be injective if and only if it's surjective. So therefore what we conclude, that option A is true. In fact, it's uniformly continuous. Option B, it is not injective. Constant functions are counter example, and we also came up with a counter example sin x. Similarly here, and option D, we also came up with the example fx equals to x plus 1 on close 0 to open infinity under the metric subspace. Clear? So do like, share and subscribe, and thank you for watching. Meet you guys soon.